as the incident wave to scatter off your surface atom or molecule, whatever you got on the surface grid, and detect the diffraction pattern emanating from this grid. Okay, so that's the general idea, and what we had in the setup is that you have a sample, you send in a low energy electron beam. Low energy means that usually under 200 electron volts, where low voltage by instruments, people standard, so it's not a very fast electron beam, it's very low. You remember around 144 electron volt. If you calculate the de Broglie wavelength, is about 1 angstrom, which is sort of what you need. Most of the surface atoms, they separate from each other is of the order 2 to 3 angstrom. So this is precisely in the same regime, so that the wavelength is in the same regime as the separation of the atom, so you can have this diffraction. So basically, you have the electron beam coming in, and then you have scattering take place, and you got this diffraction spot that you see on the phosphorus screen, which look like this, which appear like this. Okay, so and you can tune. So this is display, what they call display type lead optics. Display type lead optics. Lead stand for low energy electron diffractions. All right, so, and you can do a couple of interesting things with this. One, you can obviously tune your accelerating voltage, the voltage of the electron beam itself, and the effect of that is that you can expand and contract the spot that you see, this diffraction pattern you see. The other thing you can do is that instead of using a phosphorus screen, if you can digitize the image that you see, like actually measure the intensity of individual spot, you can generate what is called the IV curve, which we will discuss a little bit, and you can actually get quantitative information about how the atom of your surface are arranged with respect to each other. So I'm going to tell you today a little bit about this particular technique, which I think is the classic technique in looking at surfaces, because it's just like X-ray diffraction to material science, electron diffraction is to surface science. So if you talk to surface chemists, they would have something like this in their lab, just like material chemists has XRD spectrometer in their lab. Okay, so it's rather fundamental technique. So I'm going to skip a couple of pages. We talked about this last day. We talked about how the beam were connected to each other. If you are looking at a certain scattering geometry here, for example, we're looking at incident beam angle. Here, the phi angle is measured with respect to surface normal. So when phi is 0, it means normal incident into your surface itself, and you can measure those refracted beams. This is kind of refracted spot right here, and you get a formula for this, and it depends on the number of spot that you see. So n lambda, in effect, is the number of refract that you got, and as you can see, the voltage here depends on, is proportional to n squared divided by d and h. So this is the spacing, if you like, this the inter-point spacing between your atom, between the wheel space atom, and the voltage is proportional to the square of this, and it's proportional how many unit that you have. So, for example, if you have 2 unit cell or 3 unit cell, this number will change as we'll see. Okay, so today what I want to look at is that we want to look at this diffraction a little bit, and I talk about this reciprocal lattice in the X-ray diffraction. I'm going to just use that as our guide. Here we can define Receiver lattice, of course, 3-dimension. Here we have a 2-dimensional object for the surface, but we can define reciprocal neck. It's just like a receiver lattice, but you're just talking a 2-dimension. Okay, so the simplest thing to think about this is that if you take the way we generate reciprocal lattice A, B, C star, right, in the old way, you just replace the C-axis with the surface normal. Then you would get exactly the same for the reciprocal net, the 2 vector that you need to build the 2-dimensional net, which is the reciprocal net that you see in the lead objects that you got. Okay, so A star and B star are obtained from your view space vector. A and B are the view space vector that you look down in 2-dimension, and if you just think of n as your surface normal, which is normal to A and B, then you can generate this reciprocal vectors for the reciprocal net that you got. Okay, so and then you can obtain exactly the same, really exactly the same properties, if I may call this properties, which is really just A times the reciprocal lattice vector will give you 2 pi, and then if you take B times A star, right, reciprocal lattice, you get 0. The off-diagonal term, if you like, go to 0. The diagonal term B star will give you 2 pi, which is the property as what we got for reciprocal space when we talk about XRD at the time. And of course, in the 3-dimension, you also have C times C star, and that also gives you 2 pi. But in this case, there's no such thing because you are only talking about 2-dimension. And likewise, you can define something called reciprocal net vector, which is like reciprocal space vector. You remember in XRD discussion, we also have this big G, right? Big G, which is defined in terms of HKL indexes, right? Which are the mirror index, if you like, of your space, view space lattice point. Define this lattice point, and here we define in a similar fashion. A little g, reciprocal net vectors, h and k, the unit, how many unit in terms of this unit vector A star, B star, in the same manner as we have done in reciprocal space. Okay, and so what do we actually see? So in that sense, in surface reciprocal net, it's actually simpler because the amount of mathematics have been reduced to 2-dimension, and it is quite, in some ways, very easy to think about this. We have one less dimension to worry about. So let me give you an example of what we're supposed to see. Here's an example that on this side, there is the view space lattice. On this side, okay, on your right-hand side is your reciprocal space. Okay, so you normally label the center one, 0, 0. So you may ask me how do you get the center? Well, it's very simple because if you change the electron beam energy, the center spot does not move, whereas all the other spots will move, will become bigger or smaller. Okay, so that's immediately you can identify the origin, the center, essentially the spot that refracted directly back to your screen, which you don't see, of course, because you got blocked by the electron gun. Okay, so let's think a little bit about this. Here I have a view space, surface net. So these are square, arranged in a square pattern, right? So think of these as my individual surface atom. It could be nickel or something like that. Okay, and if I do an electron diffraction, what will I see? I would also see a square pattern like